Okay, Geology 105 students, this is our final lecture. We're getting towards the end of the class, obviously. I will be giving you a study guide for this week for the final exam, telling you what chapters the final exam will cover and all of those things, so be looking for that. Really no more assignments other than studying for your final exam and viewing this lecture. So yeah, we're getting really down to the bare bones here. So if you have any questions, let me know. You can text me, call me, email me, whatever you want to do. I am available for you. But today we do want to talk about our final topic, which is oceans and coastlines. And so let's jump right in and do that. So the question, and I'm gonna go through this stuff really quickly. It's hard when we're not meeting face to face, so we'll do the best we can. I'll do the best I can on my end. You do the best you can on your end, and reading the chapters and asking me any questions that you have will help fill in, I think, a lot of the gaps, if there are any. So let's talk about, where do oceans come from? And when we talked about plate tectonics, we talked about the formation of ocean basins at divergent margins, and that's basically where new ocean crust is developed, as we talked about during plate tectonics, and where oceans are formed. That basaltic crust rides lower in the asthenosphere than does the continental crust, creating on a major scale, a regional scale, these low areas. The continental crust creating the high areas, and so the high areas become the continents, the low areas become the oceans, fill in with water. So that's basically where oceans come from plate tectonics. As we said, new ocean crust rides lower in the asthenosphere. So we get that, right? I think we understand that from plate tectonics. And if you don't, go back and review that material, and I think you'll see what we talked about back then. Oceans cover roughly 75% of the Earth's surface. We all know that. We learned that back in middle school. We know that the oceans are composed of salt water. We know that the oceans can be very shallow depths. We've all waded out into the ocean at the beach, maybe gotten it up to our waist or so. So we know the ocean can be very shallow and can be very deep as well. And there are some parts of the ocean that are largely unexplored because of their depth. The largest ocean basin in the world is the Pacific Ocean Basin. And I think these are lots of facts that we already know, but let's review them anyway, right? The bigger thing that I want to talk about today are the different types of ocean circulation. There are two types that we're going to talk about. The first is surface ocean circulation. How does the water move around in the ocean basin? First of all, the shallow layer, upper layer of the ocean, called the surface layer, right? The water moves around. It moves around in what we call currents. Currents are just basically directional flow of the ocean water. We know this. These currents are driven by the wind. That's as we see there, surface currents develop from friction between the wind and the surface water. So the wind blows across the surface water. Friction between the wind and the water gets the water moving. And this causes that directional flow. Unfortunately, nature's always a little odd, and when that wind blows straight across the ocean, when the ocean water starts to move, it doesn't move parallel with the wind direction. It actually starts to turn, and that turning of the ocean currents to a direction other than the direction of the wind is caused by the Coriolis effect. And the Coriolis effect is caused by the rotation of the Earth. The Earth is a sphere, it's rotating, and because of that rotation, things that move on the surface of the Earth, including ocean currents, don't move in straight lines. In fact, in the northern hemisphere, what we find is that things turn to the right as they're moving, and in the southern hemisphere, things turn to the left as they're moving. This is again called the Coriolis effect. And what this ends up doing is, instead of ocean currents moving in straight lines, they end up moving in these large circles because they're turning to the right or turning to the left. These large circles called gyres. And there are 5 major global gyres. I'm going to show you a picture in a minute. The North Pacific and South Pacific gyres, the North Atlantic and South Atlantic gyres, and the Indian Ocean gyre. And they look like this. Notice that the ones north of the equator, they're the North Pacific gyre, and the North Atlantic gyre are rotating what? To the right, right? Because things turn to the right in the northern hemisphere. And then look in the southern hemisphere, you'll see that The South Pacific, South Atlantic gyres, and the Indian Ocean gyre, which are south of the equator, are turning what? To the left. Pretty cool stuff, but it's all because the Earth is rotating as these things are trying to move in a straight line across this rotating sphere, and that causes the things, i.e. the current in this case, to turn to the right and left. This happens with wind as well, and other things that move in straight lines across airplanes and everything, but we won't get into all that right now. Gyres, however, these rotating circular currents, they're very important to the climate because they allow heat to be redistributed. And let's go back for a second. You'll see the arrows are colored blue or red. Red indicating warm currents, blue indicating cooler currents. But look how these gyres on the left-hand side, or the currents on the left-hand side of each gyre are red arrows. Notice that. I'll look at all 5 of those gyres, and on the left-hand side, the arrows, whether they're turning left or right, are red. And what that's showing us is that hot water from the equator is being moved towards the poles. Notice that on the right-hand side of each gyre, the arrows are blue. That means cold, and you can see that that's showing where cold water from the polar areas is being carried to the equator. So do you see how heat is being redistributed around the globe based on these gyres? And that is important, folks, because without that redistribution of heat, we would not have the moderate climate that we have here, say in the mid-latitudes here in Virginia. Because of this redistribution of heat, because some heat is being carried up by the Gulf Stream current on our east coast from the equator rather, we have more moderate temperatures than we typically would at this latitude. Also, England is at a pretty high latitude if you've ever looked at England on the globe. But England has pretty moderate temperatures and pretty moderate climate as well. Why is that? Because there is a warm current, the Gulf Stream, that extends over North Atlantic Drift, that brings warm water and bathes the coast of England, okay? So, again, we see that the gyres have 4 arms. I'll go back. There's the western boundary currents. I keep hitting the wrong arrow. Western boundary currents are those red arrows on the west hand, or the left hand or west side of our gyres. We've got the eastern boundary currents. Those are the blue arrows carrying cold water on the right-hand side of each of our gyres. We've got the equatorial currents, which are the red arrows that carry warm water parallel to the equator. You see those. And then we have the drift currents, which move water laterally at higher latitudes. And you see those up there. You see right underneath where it says North Pacific Drift. You'll notice that red arrow pointing horizontal, that pointing to the right. That's a drift, right? The South Equator, or excuse me, then south, where it says South Pacific down at the bottom, that blue arrow right above, that's a drift current. Okay, so they're carrying water laterally. All right. There's another type of circulation, however, that happens, and that's called deep ocean circulation. Whereas surface circulation is caused by friction between wind and the water, surface layers of the water, deep ocean circulation is created by differences in ocean water density. Now, density itself in the ocean water is dependent upon 2 things: the temperature of the water and the salinity, or the dissolved salts in the water. As temperature decreases, density of water increases. So let me say that again. As temperature decreases, density of the water increases. As salinity increases, density of the water increases. In other words, as you dissolve more salts in the water, the density of the water goes up. So our densest water, right, is water that is very cold but has a lot of salt in it. Okay? Now, deep ocean circulation, we'll get back to that in a second. And deep ocean circulation is idealized through the idea of something we call in science the thermohaline circulation. It's also known as the conveyor belt model. And what it looks like is this. And what it says is that water is redistributed in the deep ocean layers by sinking and rising water. Because if we're talking about density, of the water, Then dense water sinks, less dense water rises, right? So in deep ocean circulation, our cold, dense water sinks and our warmer, saline, depleted water rises, creating this mixing effect vertically within the ocean. So that's what thermohaline circulation is. This diagram here is showing that the red parts of the conveyor belt there are showing warm water that has risen and is flowing near the surface of the ocean. And then the blue parts of the conveyor belt model there are cold water that has sunk to the bottom of the ocean and is riding around at the bottom of the ocean. So you'll see that around Greenland there in the North Atlantic is where red turns into blue, which means that you're having sinking water there. You also see sinking water near Antarctica. You see rising water in the North Pacific, so where our blue arrow, you can see the little white arrow showing the direction of flow. Where blue rises to the top and becomes red, right? It happens again in the Indian Ocean there as well. So this is idealized. It's not meaning that water molecules are actually following this conveyor belt, but this is an idealized model of what thermohaline circulation might look like if we did follow a little water molecule around in an idealized state. Like surface currents, thermohaline circulation redistributes heat around the globe, so it's very, very important. So again, we're taking warm water and moving it around. We're taking cold water and moving it around, redistributing heat around the world. The idealized version of thermohaline circulation starts in the North Atlantic and ends in the North Pacific. So look in here, you see in the North Atlantic right there south of Greenland, we have the sinking of the water. It goes down, makes its way down through the Atlantic Ocean, over past Antarctica, up into the Pacific, and then rises in the North Pacific, comes back as a warm current all the way across the Indian Ocean, all the way up the Atlantic again, and then goes back up to the North Atlantic where it sinks again. That's the idealized version. Then you have the Indian Ocean in there, kind of complicating things, but that's the idealized version of this mixing, and it happens more vertically than it does laterally. Surface currents move water laterally around. Thermohaline circulation moves water laterally as well, but also vertically. Okay. Thermohaline circulation is a little difficult to understand, so just do your best with it, but understand that it's part of the deep ocean circulation, and it redistributes heat. Those are the two main things I want you to know. We all know that there are ocean waves. As we've all been to the beach, we've seen the waves come in and crash on the beach. And so waves are the main means of transferring energy through the surface layer of the ocean. So again, they're created by the wind. As the wind comes along, it creates these undulations in the surface of the ocean that transfer energy from one place to another. We know that waves consist of troughs and crests. We've all seen that. The geometry of a wave, or the anatomy of a wave, is wave height, which is the vertical measure between the bottom of the trough of a wave and the peak of the crest of the wave. So it's how tall the wave is from bottom to top. Wavelength is the horizontal measure between successive crests. So if I know where one crest is and I move laterally over to the very next crest in a wave, that length is called the wavelength. A wave period is simply the time that it takes for one wave to pass a certain point. So if I had a stopwatch in my hand and I started it when one crest passed me, and when the very next crest came by, I stopped the stopwatch, that period of time is called the wave period. Wave frequency is just an inverse of period. It's the number of waves that pass a certain point in a given amount of time. So if I were to say, okay, how many waves are going to pass me in 1 minute? And I start my stopwatch and I count 1, 2, 3, 4, 5, 6, 7, and I stop my stopwatch at 1 minute, and then I say, okay, how many waves passed? And I say 27. Well, then my frequency would be 27 waves per minute, right? Usually waves are calculated per second, but we won't go there. All right. Oh, it's a lot of stuff, isn't it? All right. Now, wave height, how tall a wave is, wavelength, how long a wave is, wave period, and wave frequency, all these things we just talked about, are dependent upon 3 factors, and that is wind speed, fetch, and the length of time that the wind blows. In other words, how big our waves get depend on how hard the wind's blowing, wind speed. That kind of stands to reason, right? The fetch, the distance over which the over the ocean surface over which the wind blows. So if the wind's blowing over a small area of the ocean, we're not going to get big waves. If wind's blowing over a very large area of the ocean, we're going to get bigger waves. And also the length of time the wind blows. If the wind blows for just a few minutes, it's not going to create big waves. If it blows for a few days, it can create tremendously big waves. Folks, this is why hurricanes create such big waves, because they have high wind speed, high fetch. In other words, hurricanes happen over large areas of the ocean, and they blow for days and weeks at a time, and creating big waves. For all these reasons, you get big waves. Okay? However, when we look at, I know I'm moving through this stuff quickly, folks, but I don't want to beat a dead horse, and I'm staring at a microphone and a screen as I talk, so I can't interact with you very much. So I'm just going to keep plugging away. You can pause and rewind or whatever you need to do. Water motion. When we look at the microscopic motion of an ocean wave, we notice that things move in a circular motion. In fact, it looks something like this. Notice those little light blue circles there. Water molecules don't actually move in a linear fashion from point A to point B in a typical water wave. They move in circles. So the water, as the wave passes, it's not taking water molecules and moving them to the right or to the left or miles and miles down the wave. It's just moving in tiny little circles. As the wave passes, tiny little circles. Those tiny little circles of water molecule movement get smaller and smaller as you go down, because the wind effect gets less and less, right? The wind's going to be most effective at the very surface and gets less and less effective as you go down. So those circles decrease with depth. Where the circle motion ceases, we call that wave base. So you'll see down there that little horizontal black line that says wave base equals half the wavelength. That's wave base. So that's where the wave action stops having an effect on the water. So winds no longer have an effect at that depth. The little circles stop. And wave base is half the wavelength. So if we look at the wavelengths, and you see the wavelength is marked up there from crest to crest, half of that is the depth of wave base. Okay? Below wave base, you don't have the effect of the wind anymore. The water isn't churning. The waves aren't churning the water up. However, and so if we look at our diagram here to the right, as we see, the waves are very symmetrical looking off the coast because wave base is not touching the bottom of the ocean. However, as those waves move onshore, look, waves start to interact with the land surface as the water shallows, and then so you got friction with the smallest circles at the bottom near wave base. The bigger circles up top have less friction with the bottom, and so they continue to move faster, while the smaller circles at the bottom move slower, causes the wave to actually become asymmetrical and start leaning, and it continues to lean as more and more friction is encountered as the water shallows, and then we finally get a breaking wave near the shore. This is why waves break at the beach. Okay? It's all about wave base. It's all about that base, right? Oh boy. Okay. Let's talk about, and again, I know you can pause if you need to and go find this in the book and review, but I'm going to move on here. Shoreline features and processes. There's two things that happen on a shoreline: erosion and deposition. They don't happen at the same time, but they do happen along a coastline. So let's talk about erosion first. Wave erosion, when a wave breaks, the energy is used to erode material. We know this. We've seen this at the beach. And then the material is carried away and deposited somewhere else later. As waves come onshore, there's something called wave refraction. I'm not going to try to demonstrate what this is. I'm just going to describe it. Your book probably talks about it a little bit, and if not, you might just look up wave refraction on YouTube. You can find maybe something that'll demonstrate visually what it is. But let me just describe it. A wave refraction is the bending of ocean waves as they approach a shore. Lines of ocean waves approach at a certain angle, but as they get closer and closer on shore, they kind of turn and parallel the shoreline, no matter the approach angle. And what this does is this helps concentrate wave energy on prominent coastal features, so things that are sticking out. And it leads to a straightening of the coastline. So what do I mean by that? So look at this diagram here. On the left, diagram A, the waves are approaching, right? But notice how as they approach this uneven shoreline, they start to bend into the shape of the shoreline. Notice how the waves that are coming in are kind of wrapping themselves around this prominent. They're trying to get parallel to the shoreline. And over time, that concentrates wave energy on that prominence. And over time, what diagram B is showing you is that the prominence gets eroded away and we start to straighten out the shoreline. This is called wave refraction. So waves, as they approach, try to parallel themselves with the shoreline. This causes a concentration of energy, which results in a straightening of the shoreline. All right. Longshore current, because waves don't approach at because as waves approach, they usually don't approach parallel. They approach at an angle to the shoreline and then kind of turn themselves and become parallel. Because they initially approach at an angle, they creates what's called a longshore current. This is a directional parallel flow of current that's parallel to the coastline. It's a vector of the approach current if you understand vectors. If not, don't worry about it. Just understand that longshore current is parallel to the coastline. The great thing about longshore current is it can move a tremendous amount of sediment. It can also move sediment via what something's called a beach drift, which is a zigzag pattern on the beach. So let me try to describe this. So if we look at longshore drift, first of all, we've got our longshore current. If you see where it says surf zone down there in the blue, notice that red arrow pointing, series of red arrows pointing to the right there. That's longshore current. So it's just off the coast and it parallels the coastline and it carries a tremendous amount of sediment from one place to another. But something else carries sediment downstream as well, and it's this zigzag beach drift. And you'll notice these little curved arrows up in the brown area. And what they're showing is as those waves that are the blue lines you see towards the bottom of the diagram, as they approach, they're going to carry sediment. They're going to wash up on shore and carry sediment up on shore at an angle. But when that sediment stops and the water stops and then it rushes back to the ocean, it's going to go straight back into the ocean, right? So as the water carries material up at an angle but then brings it back straight into the ocean, it's slowly moving material downstream, right? Or down coast, I should say. So you've got longshore current and beach drift. They're two different things, but they're very much related to one another. But they both carry sediment down shore. There's also something known as a rip current, and most of you have heard about this because you see signs on it at the beach, right? It's a strong seaward current that's produced usually when there's a dip or a valley in the underwater topography that's oriented perpendicular to the shoreline, or where two longshore currents collide. But in either case, what happens is as the water rushes offshore, so we're standing on the beach looking out to the ocean, as it rushes offshore, it's somehow channelized. If you see the lighter blue or green area where the black arrows are in this diagram, you'll notice that that's underneath the water. There might be a little channel or a little stream channel or something, a depression of some sort. And the water gets concentrated in there and kind of rushes off, and it can create a very, very strong offshore current. And these are known as rip currents. And again, you've seen signs of these at the beach, and you probably sort of understand what they are. And if not, again, I'm sorry, folks. I wish I had a board and I could draw it out for you. But I just don't have that ability right now. All right. Let's talk about shoreline features and processes. Let's talk about erosional processes first, since we've been talking about those. There are things called wave-cut platforms, wave-cut cliffs, marine terraces, sea arches, and sea stacks, and I'll try to describe these as briefly as I can. But wave-cut platforms are just as waves crash on the shore, they cut away rock, they erode material. And they typically will erode away flat areas, just like this. This is a wave-cut platform. And where that wave-cut platform stops landward, and you get a cliff, right? I mean, it stands to reason. All this is erosion from wave action, waves crashing on the shoreline. So that takes care of two of our things there, right? Wave-cut platforms and wave-cut cliffs. Marine terraces are basically just step-down wave cut platforms. So let's say we had this scenario here where the waves are crashing and creating this platform and these cliffs. But let's say sea level drops, let's say to where we see the sea level right now in this picture, and it stays there. It doesn't want, this is probably low tide in reality, but let's say the sea level stays right there. The waves are going to crash in that area just to the right of what we're seeing here, creating another wave cut platform and another series of, or another wave cut cliff just to the right of this. So then if the sea level drops again, what we would see is the wave cut platform that we see now, and then a step down wave cut platform to the right of that. And then we could have another one step down after that. It's creating these terraces, right? So that's what wave cut, or excuse me, marine terraces are. Sea arches are when prominence, things that are sticking out into the ocean, kind of get eroded from the left and the right, and at some point you get a cavern that forms in between. Let me go back and describe this a little bit better. Remember this picture here? Notice that you got the concentration on diagram A there. You got the concentration on that prominence. Well, as the prominence erodes from the right and from the left, that prominence is going to get narrower and narrower and narrower until it could get narrow enough where a little alleyway or a little doorway forms in between. And that would be a sea arch. And a sea arch looks like that. If the arch part of the sea arch falls away and there's just a rock pillar in the middle of, in the ocean, that piece to the left becomes not an arch but a pillar, then we call that a wave or a sea stack. Okay, so there you have wave cut platforms, cliffs, marine terraces, sea arches, and sea stacks. Those are erosional features. Let's talk about depositional shoreline features. There's a beach, which we all know is sand that's deposited on the shoreline. We've all been to the beach. That sand is brought there, a combination of river deposition and ocean wave deposition. Spits are tongue-shaped sands, bars extending from a prominent land into the mouth of a bay. If we look at this section here, you'll see where the spits are indicated. They have like a tongue shape, curly shape to them. This is all deposition. Bay mouth bars are a bar of sand that completely blocks the mouth of a bay. You'll see, they call them a bay barrier here in this diagram. You'll see that. Okay. A tombolo is sand that connects the mainland with an island or a sea stack. There's a tombolo on the left. There's that island out there. You can see the sand that connects the mainland to the island. That's a tombolo. And then a barrier island is a large depositional ridge that parallels the coast and acts as a storm barrier from the mainland. This doesn't have a picture of one, but this is a picture of a barrier island here. If you've ever been to Atlantic City, New Jersey, Ocean City, Maryland, Nags Head, North Carolina? Yeah, I think it is. Yep. Then all of those are barrier islands. Obviously, because erosion and deposition are happening, we want to stabilize our shorelines. And the amount of shoreline stabilization that's required in any area is dependent upon how much sediment's being brought from the local rivers, the local tectonic activity, weather patterns in the area, wave patterns and longshore current in the area, and the shape of the coastline, right? All that will affect how much shoreline stabilization is required. So how do we stabilize the shoreline? How do we keep sediment from moving around? We can do it using lots of things. Groins or jetties. These are structures that run perpendicular to the shoreline and trap sediment. This is an example of a groin or a jetty. A jetty is basically just a long groin, but imagine the Longshore Current is going along parallel to the coastline. It runs into one of these things. It's going to slow down and drop its sediment, right? And not transport it downrange. Breakwaters are just barriers placed offshore to dissipate wave energy. So the waves are coming in. So what do people, you can put breakwaters out there, piles of rocks or cement, whatever, and it slows down the waves so that by the time they reach the shoreline, they don't break as hard and don't cause as much erosion. Seawalls do the same thing, except they're walls that are built right against the coastline, so the waves crash against these artificial man-made walls instead of against the coastline, therefore decreasing erosion. Beach nourishment. When we add sand to the beach or a sediment to the beach, that's not really, it's a stabilization technique, but you're not getting rid of erosion. You're just bringing artificial deposition to the place to replace what is eroded away, right? Land extension, building land out into the ocean is a way to stabilize the shoreline. Again, you're artificially adding things. And then, of course, this isn't really stabilization, but it's worth mentioning that we can also relocate. If you're having trouble keeping your hotel from falling into the ocean, then move your hotel. Again, a growing or jetty. This is a seawall, right, built right against the coastline. All right, we're moving fast, aren't we? I apologize, folks, but this is what we got to do. It's our last lecture, though. Hang in there. Let's talk about tides. We've all heard of tides before, right? Tides are fluctuation in the elevation of the ocean surface due to the gravitational forces acting on ocean water from astronomical sources, the main two being the moon and the sun. Now, other planets in the solar system do affect our tides. However, their effect is minimal. The moon and the sun are the primary and secondary. And notice that the moon is the primary. Even though the sun is so much larger than us and the moon, it's so far away that its effect is less than the moon, which is only 250,000 miles away. So it's very, very close. But as the moon pulls on the Earth, the pink there is an idealized version of the bulge of the ocean, right? So it pulls the ocean water towards it and, ironically enough, pushes on the opposite side of the Earth, pushes the ocean water away. So it thickens the ocean water in the direction and the opposite direction of the moon and thins it perpendicular. Notice that at the poles, north and south on this sketch, the layer of water is thinned out. Again, the water is noted here by the pink area. We call that bulge towards the moon the tidal bulge. The sun has a very similar bulge. Its bulge is not as big because, again, the sun is has a secondary effect on the tides of the Earth, but it still has its own bulge. There's two types of tides. One's called spring tide, one's called neap tide. Spring tide is when the moon and the sun are aligned with one another. Therefore, the gravitational forces of the moon and the sun are in phase and compound on one another. In other words, the bulge is as big as it'll ever be. That means you get the highest high tides and the lowest low tides of the month. You can always tell when you're in spring tide by the new moon and the full moon, because that's when we see these types of tides. I should say, when we look at this diagram, I didn't say this before, remember that the Earth is rotating within this bulge, right? So as the Earth rotates, places are going to go in and out of the tidal bulge. And you got to think three-dimensionally here too. There's also a thinning right here over South America. If you see South America there'd be a thinning there and a thinning on the opposite side that we can't see in this diagram as well, right? The bulge is going to happen just in that area towards the sun and directly away from the sun. Every other place is going to thin out a little bit. So three-dimensionally, we also get a thinning on South America in this diagram and a thinning on the opposite side as well. So imagine as the Earth rotates and South America rotates from the position it's in now into the bulge, then it's going to go from low tide to high tide, right? Neap tide, let me show you. So this is spring tide. Notice that the sun is off to the left off the page. We can't see it. And the moon is to the right. They're in phase. They're in line with one another. So the moon, Earth, sun are all in line with one another. So the bulge is as big as it's going to be. So we get the highest high tides and the lowest low tides. However, during neap tide, which is when the sun and moon are at 90 degrees of alignment to one another, this is where gravitational forces are out of phase. So the sun is pulling a bulge not in the opposite direction of the moon, but 90 degrees to the direction of the moon, which means we get the lowest high tides and the highest low tides of the month. This happens during the first and third quarter phases of the moon. So that looks like this. So we got the sun off to the left again, the moon up to the top. Notice how the bulges kind of cancel each other out because the sun is trying to thin or thicken bulge left and right. The moon is trying to bulge top and bottom. So those bulges work against each other, and we get the lowest high tides and the highest low tides. That's called neap tide. Particular influences on tide in any given area, though, are not just about the bulges. Shape of the shoreline, shape of the ocean basin in that area, depth of the water in that area, the monthly tidal cycle of that area, and other astronomical factors such as perigee and apogee, which you can look up on your own if you want to know what those are. All of these things influence tide as well in a localized area. So tides are pretty complex, but there are three basic tidal patterns that we see. There's the diurnal, the semi-diurnal, and the mixed tide pattern. Diurnal is when you have one high tide and one low tide per day. So you have one high tide in the area, about 12 hours later you have a low tide, and that's it. Semi-diurnal is when you have two high tides and two low tides a day, which is pretty typical, and they're roughly the same height. So you have a high tide, a low tide, a high tide, a low tide each day. The two high tides are about the same water depth, and the two low tides are about the same water depth. The difference between mixed and semi-diurnal is that in a mixed tide you have two high tides and two low tides, but they're not of the same height. If we want to look at this graphically, we would see the diurnal phase is the first diagram there. The second one, top right, notice that that's semi-diurnal. So we get two high tides and two low tides, but notice that the levels of those are pretty much the same. But in a mixed tidal system, we get two highs and two lows. But look how different those depths are. Okay. When you're talking about tides also create a directional flow as they come in and go out, ebb and flood. You've probably heard those terms. Ebb is a seaward movement of the water during a transition from to low tide, so when you're going from high tide to low tide. And a flood is when you're going from low tide to high tide, so the water's moving on land. So water moves off, that's ebb tide. Water moves on during high tide, that's flood. And that creates a lateral movement of water, directional flow, that can actually be harnessed for energy. We see that France has done a lot of work. I think Arriva in France actually has done some work with generating energy and power through the tidal movement of water. But anyway, we blew through that, folks. I know we did. But you can pause. You can go back. You can listen to it again. You can read your book. You can ask me questions. You can go on YouTube. You can go on learner.org and look at Earth Revealed videos. I mean, there's a million ways that we can, you can reinforce this material. But one thing I don't want you to do is not understand it. So if you're having trouble understanding it for whatever reason, call me, text me, whatever, email me, and we'll figure it out. All right? Hey, listen, I've enjoyed this semester. I thank you so much for being a great class. I'm sorry that it, halfway through we had to switch gears and do it remotely. But that's life, right? We have to work with exigencies in life. Things happen, and we roll with them. Thank you for being a good, flexible class. Thank you for all your hard work. If I can ever be of help to you, please let me know. I am here for you, even after this class ends. All right? I care about you, and I want to see you successful in life. So reach out if you need me. All right? I will talk to you later. Have a good one.